Hey everybody, Dr. Retzik here. This is our final video in Chapter 14. It's a continuation of Section 14.7. Let's get started. The purpose of today's video is to do a single example of finding maxes and mins where the domain of the function is what's called a compact set. And all that really means is closed and bounded. So closed in the sense that it contains all its boundary points, and bounded in the sense that you could draw a circle around it. So rather than thinking about a surface floating over the entire xy plane, we're just being a little more restrictive. Let's do the example. So we're trying to find the absolute max and min of the function f of xy equals x squared minus 2xy plus 2y on the domain of all points on or within the triangle with vertices 0, 0, 0, 2, and 3, 2. And if you were trying to draw that region in the xy plane, I guess it's this region here. So this is just the xy plane. We are not attempting to sketch the surface in this drawing. We're just interested in the domain. And I would say that domain is this here. Where that's 3 and that's 2. And the region we're interested in is this region here. Boundary included. So that's the domain that we're going for. And we're trying to figure out where this function, f of xy equals x squared minus 2xy plus 2y, comes out biggest and smallest on that domain. Now, we have an expectation that there is a highest and lowest point on the surface over that domain by what's called the extreme value theorem that you've read about in 14.7. It says if your function's continuous, which ours is, and your domain is closed and bounded, which ours is, then the function actually achieves its highest and lowest points somewhere on that domain. We're trying to find out where that happens. Okay, so problems like this where you're trying to find the extreme values of a function on a compact domain really are broken into two pieces. The first piece is to try to find the critical points inside the domain on the interior of the region. And that goes exactly as it went in the first video of 14.7. So let's write down the gradient of this function little f. So you put the x partial, 2x, take away 2y in the first coordinate. And you put the y partial, negative 2x plus 2. In the second coordinate. And remember, for local maxes and mins, when you're not worried about whether it's the overall max or the overall min, your candidates for locations of local maxes and mins are simply critical points of the function f. And critical points are points where the gradient is 0, that's where a tangent plane is horizontal, or else points where the gradient fails to exist, like maybe at the sharp corner at the top of a witch's hat. In the present example, you can see the gradient exists everywhere, and if we're interested in where that gradient comes out 0, well then on account of that piece of the gradient comes out 0 implies that x is equal to 1, and once x is equal to 1, if the first entry is 0, y has to be 1 also. So summarizing, the gradient of f comes out to 0 only at the point 1, 1, which is in our region and is about right here. So it looks like we have one critical point inside the region. The value of the function at that point is easy to compute. If you stick 1, 1 into the function, then you get, let's see, 1 plus 1. Fantastic. So we found one critical point inside the region, and we know what the function comes out to there. Now, we could go and do second derivatives test right here and actually decide whether at that red point, 1, 1, we had a local max, local min, saddle, or no information. I actually went off to the side and did that. I'm going to hold out on that answer because it doesn't matter right now. That is the one spot where we could conceivably have a max or a min inside the region. We will now compare that spot and the function's value there to what the function comes out to on the boundary of the region. Now you can see the boundary consists of 3 pieces. Can we call this piece L1 and this piece L2 and this piece L3? Each of these problems, when you assess the boundary, becomes 3 or more, depending on how many edges the boundary has. Calc 1 max-min problems. Let's look at the piece L1 of the boundary to see what kind of Calc 1 max-min problem we're looking at on just that piece. Okay, so here we go. Stay organized. On L1, what are we looking at here? Well, we're trying to see what the function comes out to at points on L1. Points on L1 are all of the form 0, y, which if you plug 0, y into the function, you get 2y. And we're interested in this on L1 for y values between 0 and 2. Now, this is not a very hard Calc 1 problem. If I came to you and I said, hey, what's the biggest 2y can come out for y values between 0 and 2, you guys would answer immediately. You would say, well, the max is 4, and that happens when y is 2. And if I said, what's the smallest 2y can come out for y values between 0 and 2, you guys would answer immediately. You'd say, all right, the min is 0 and happens when y is 0. Which means back on our drawing, as far as L1 is concerned, the least f comes out is right there, where f comes out to 0. And the most f comes out is right here, where f comes out to 4. Okay, so now we know the value of f at 3 important locations. We know that at the interior critical point, the function comes out to 1. We know on the piece of the boundary called L1 the biggest the function comes out is 4, and the smallest the function comes out is 0. Let's move on and assess L2. So now, totally separate problem. On L2, well, we're interested in what the function comes out to on L2, and every point on L2 is of the form x over 2 up. And if you plug that in, when the dust settles, you get quantity x minus 2 squared. And we're interested in that quantity for x values between 0 and 3. Those are the x values along L2. Okay, and again, if I came to you and I said, hey, what's the biggest quantity x minus 2 squared comes out for x's between 0 and 3? You'd be like, well, that's going to happen when the stuff in the parentheses is of greatest absolute value. This is a parabola opening upward, so it has to happen at one of the endpoints. Let's test them. If you stick in x equals 0, you get 4. If you stick in x equals 3, you get 1. And then the min, well, that's when the stuff in the parentheses would be as small as possible in absolute value, and that happens when x is 2. So summarizing, you know for sure on L2, the max is 4, and that happens at x equals 0. And the min is 0, and that happens when x is 2. Now, it feels like we understand f's behavior at 2 more points. I don't think we do. It's really 1 more point, because look at this point. On L2, the spot where we found out the max came out to 4 was when x equals 0. That is still this dot. And then we also found out that the min along L2 happened when x is equal to 2. So maybe right about there. And we found out that the minimum value that occurs along L2 at that spot where x is 2 is 0. Okay, one last part of the boundary to check. Let's move on to L3. Now L3 provides an additional morsel that will be useful here in the second half of 14.7. On L3, well, look at L3. What is that? L3, what is that? That's the line y equals 2/3 x. So on L3, if we're interested in what the function comes out to, we're plugging in points of the form x over 2/3 x up. Now, if you stick that into the function, plug that in for f of x comma y, when the dust settles, you have 1 minus 1/3, x squared plus 4/3 x. And we're interested in that for x values, again, between 0 and 3. Now, if I came to you and said, what is the max that minus 1/3 x squared plus 4/3 x comes out to for x's between 0 and 3? I feel like this piece of the boundary is harder. You didn't need calculus at all on L1 and L2. That's great. But if you come to a piece of the boundary where assessing the max and min is a little bit harder, well, you guys are excellent at Calc 1. You are masters of functions of one variable. So if you're interested in the biggest and smallest, that comes out, then you do a little mini Calc 1 problem on that function of just x. So I'm going to say something like, let little g of x be the quantity of interest And if I said to you, hey, how do you find the max and min of G on the interval from 0 to 3, and it were Calc 1 class, you'd say, well, I would find the critical points and check the endpoints. G prime of x is minus 2/3 x plus 4/3. So you can see only CP is when x equals 2, and when x equals 2, y you can see equals 4/3 because y is 2/3 x. At that point, g of 2, go ahead and plug that in. You get minus 4/3 plus 8/3, so positive 4/3. G at the far left of the interval from 0 to 3 is 0. And G at the far right of the interval is, what, minus 9/3 plus 12/3 is 3/3 is 1. So now you know the value of the function g, which is equal to the function f along L3 at 3 important points. Back in the picture, the 3 points are when x is 0, that's here on L3. When x is 2, that's there on L3. And when x is 3, that's there on L3. Our analysis of the 3 sections of the boundary is telling us what the function comes out to at each of those dots. So now let's make a list. All right, here we go. At this dot, f came out to 4. At this dot, f came out to 0. At this dot, f came out to 1. At this dot, f came out to 4/3. At this dot, f came out to 0. And at the interior point, f came out to 1. And now the beauty of this is, that's it. No further analysis required. You want to know the max that f ever comes out? Look at the list. So go ahead, look at it. What's the biggest f ever comes out? Looks like 4. What's the smallest f ever comes out? Looks like 0. And then those other values may or may not be local mins, local maxes, saddle points, whatever, but they're not relevant as far as absolute max and absolute min are concerned. So our grand conclusion is, thus, absolute max of f is f of 0 over 2 up equals 4. So that's the most f ever comes out. And absolute min of f is f at, oh, that happened at a couple spots, 2, 2, and also at 0, 0, and that common minimum value that f came out to at those spots was 0. And that's it. You have found the absolute maxes and mins by a 2-step process. Find the critical points interior to the region and consider them as candidates, and then break the boundary of the region into as many pieces as necessary. Analyze each of those pieces using calculus of one variable if necessary, and find the maxes and mins on each of those pieces. And then on that long list of maxes and mins, the biggest max is the absolute max, and the smallest min is the absolute min. All right, that's it for chapter 14. that's it for optimization. You will encounter some word problems where you have to kind of build the function that you're trying to find the max or min of. But in terms of the analysis itself, once you have the function and you know the domain, then 14.7 gives you the techniques to find maxes and mins. All right, that's it for Chapter 7. Come in with questions on Tuesday, and let's get prepped for Wednesday's midterm. Okay, see you next time.